So hi everyone, welcome to lecture 12 of CUDA mode. Today I'm super thrilled to have one of our very own mods, Thomas Viewman, to talk about FlashAttention. This is probably I guess the hottest CUDA kernel out there today. So I'm really thrilled to have someone as deep as Thomas to come talk to us about today. So yeah, Thomas, please take it away, and I'll mute myself.
Yes, so I label this Introduction to FlashAttention. So I'm short selling you a bit if you wanted to have live coding of the fastest FlashAttention kernel, because I was a bit foolishly ambitious about the timing here. There's only 1 week between GTC and now. But hopefully it will be something of interest, and it'll be a bit of a progress report. Obviously, since last time, I think I spoke more or less 8 weeks ago, plus or minus 1 hour, depending on whether you're on daylight saving time. And so nowadays I do Thunder at Lightning AI, and I'll use this talk to plug that a bit too during the code demo. Okay, so let's dive right in. This is something I showed you 8 weeks ago too, when we first discussed tiling. And so FlashAttention kind of takes the attention and takes quite a computation, which involves two mud molds and a softmax, and applies a similar basic tiling scheme to it as you do for the mud molds. But obviously it has been optimized quite a lot, because it is one of the things that consumes time and also GPU RAM in the transformer models that basically eat all the compute that is available right now. And so the basic idea here is again, try to avoid writing intermediates to RAM, and we'll see a bit how we're getting to that. Okay, so this is also a slide from 8 weeks ago. Obviously, we want to avoid writing things to DRAM and loading it back. If we can avoid allocating memory and keeping that around for a long time, that's an obvious win, because we never have enough GPU memory. But also the shared memory, the SRAM here, is quite a bit faster, usually in the order of 1 magnitude, although you always have to kind of update your assumptions in these things, similar to the overall scheme that, when I started with PyTorch 7 years ago, you could basically saturate a GPU with just sending one kernel after another. Things have changed a lot. Before we dive into how FlashAttention is implemented, obviously you're all into CUDA programming a lot, and you're quite likely all into AI. But let's very briefly recap what attention is, what that operation is that we're trying to compute here. And so I like to think about attention a bit as a classification thing that is inside our model. And so if you think about the typical classification head in a network with some hidden size D and C classes, for people that are old enough to have been around when ResNets were a thing, we had these convolutional things, and then at the top there was a final layer, there was a linear layer, a fully connected layer, and then was the softmax to get probabilities. And so this is what we have here. We have d-dimensional input activations, Then we have this final layer, and I'm calling it K for reasons, that multiplied to the activations, the inputs, gives us some lockets, and we apply softmax to get probabilities. So far, this is pretty standard, but we can look at this, we can rearrange things a bit. And so a long time ago, if you look at my blog, Learn Apparat, I have a blog post like how many models is ResNet, where I'm trying to tell you that it's actually 2 models, because we can take this final linear layer and consider it as class embeddings. By not thinking about it, you put a vector in, and then you get like class lockets. But you can also think about it that each row of that matrix is an embedding of one of the target classes, and then you take the scalar product of these embeddings to get lockets, and then you take softmax again to get the class probabilities. And what I did here is I added this scaling term that will be also in the attention, but which is just a temperature term of sorts that in the olden days you would probably try to find an initialization that essentially provides this term for us. Okay, now if we have here Q and K coming not like from these things, but coming from linear operations, this is just the attention weight. And so the attention is a classification problem of which rows of VS of the value part of the attention should we pick. So this is, I think about attention like as a component of neural networks. But now we want to go and make that fast, because before it was like the most time-consuming operation in transformers by far. And so here's the thing about multi-head attention. That was the basic attention mechanism for one head that I just showed you. When you have multi-head attention, you have multiple classifications of this type, and the D gets smaller, and you have that simultaneously. And if you look at the attention is all you need paper, the classic one that introduced BERT, they write multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. So they propose that or present that as a purely like a thing that they want to have for the representational performance, but it also is a formidable computational simplification in the sense that the heads are fully independently. So like the batch dimension, when you feed multiple examples at once, these are fully independent, and you can parallelize them very easily because of their independence. So we have actually a huge simplification here. And in fact, if you look at like the things that constrain us in a bit, this has been like a happy little accident, if you believe that it's like not invented also because of the computational complexity it saves. But so it's really great that we have multiple heads, because the size of each head will be a limiting factor, and having more heads like lets us parallelize really easy. And this is maybe already the the next thing. So when we think about how to write attention on the GPU, this embarrassingly parallel part, if we have enough items to calculate, like enough attention heads and a large enough batch size, we can distribute those in order to use all the streaming processors that our GPU has. And so one head will be calculated in one block because there's too much interdependence in order to.
Want to give us just a really, really short intro?
Is there? Sorry. Okay. So typically the FlashAttention trick will try to compute like one attention head's computation in one block on the GPU, so we can share memory between all of these. So we further assume here that query key and value have the same shape, which is not necessarily always the case. You could have key and value of different sizes than the query. But we assume here that each has sequence length n and head dimension of d. And the other thing we need is we need the softmax operation, and so the computation just fits in one line. P is the probability weights, is the softmax of the query times the key, times the scaling factor, and then the output is a matrix multiplication of this weight matrix with V. We will see that through lots of, happy coincidences or what, we can actually avoid materializing P, which is an intermediate here. And again, I've studied mathematics a long time ago, and back then when you did numerical linear algebra, the saying was, for large matrices in certain contexts, if you materialize your intermediate matrix, you're doing something wrong, because that was prohibitively expensive in terms of memory. And so we're in a very similar situation here, where we want to try to avoid materializing this intermediate.
So Thomas, before you keep going, I said a quick clarifying question on your very first line, which was, I'm still having trouble mapping what you're saying around no, just the next slide. Next line. This is the slide you were on earlier, after.
This one?
No, one more. The one you were at when I first started asking my question.
Sorry, I didn't.
One more?
It was too low volume.
Oh, I see. One more? Yeah, here. So on the very first line here, I'm having trouble what you're saying, mapping ahead to the hardware. So I was wondering, you're basically mapping ahead per SM. What do you mean by block here? So I was wondering if you could elaborate on that first line.
Okay. So when we when we launch CUDA kernels, we define a grid of blocks. And the blocks are the cooperating threads. And so the idea is, if we have 80-something streaming multiprocessors, and a block is always processed by a single one of them, we want to have enough blocks to saturate all these 80-something streaming multiprocessors. And so we want we will calculate one head in one block of cooperating threads that run necessarily, because they want to use shared memory. This runs on one streaming multiprocessor. And so kind of the fact that we have many heads and many batch items, hopefully, that saves us from only utilizing part of the GPU.
And
Obviously, you could then do other tricks to get better utilization, but this is the basic idea here.
and presumably this is the reason why like the head dimension in FlashAttention is so small and fixed. Basically, it's like 128 to 56, because otherwise you couldn't map a head to a block, and it just makes the algorithm break down. Is that also your understanding?
Yeah, basically, and we will see this, and I'm still struggling with it. So I tried, and I did implement like a little toy kernel that implements attention for one head, and I'm still like way slower than even non-sophisticated flash attention implementations, and we'll see just what are the limiting factors in a bit. So yeah, great question. But yeah, the reason why, or the largest constraint is, to my mind, is the dimension here of each individual head, because that will restrict like the registers we have or the shared memory. In fact, we will have such a need for shared memory that we try to move things from shared memory to registers in a bit. So
So speaking of like this, because this really reminds me of a point Christian Perch, who's a PyTorch core developer, made to me, which is like if you look at the formula for multi-headed attention, you have a matmul, nonlinearity, matmul. And so conceptually, there's almost no difference between multi-headed attention versus a two-layer neural network with a nonlinearity. And the main difference is basically that you have a small head dimension. And I thought that was a very interesting point. So, yeah, I'll shut up
yeah.
now. I'll stop it with my comments.
Yeah, so in this sense, that's a great observation by Christian, and a very succinct way to also what I try to elaborate on, like how to view the attention, is, yeah, this is like a small two-layer network, but with a very large batch size due to the heads. So we trade heads, trade like batch size like things for the inner hidden dimensions, and we desperately need that. Okay, so let's look at the tiling strategy, and so I've tried to like when I try to implement CUDA kernels, they don't always turn out to be very fast. But so the first thing I try to look at is like, what does it take to compute one element of the output? And that's like usually a good strategy to try to have like one thread needs to compute one or more outputs. That would be the ideal thing, because multiple threads working on the same output always has a synchronization problem that you need these atomic adds or things like that. And usually that's not a good idea, because if you have lots of them, they will run into performance trouble. And it also always presents you with these nonlinearity, with the non-determinism, where when you run the thing twice on the same GPU on the same day, you get different results. They will be just slightly different from the addition order, but they will be different. So here we go and think about what does it need to compute one element. And so the element has a sequence dimension, which I'm calling T here. And the D dimension is like the hidden layer, like one head. Think about it as 128, if you like, Llama 2, 7 billion. Okay, so in order to compute this, I need the value. And this I need for all the sequence elements S, and for all the Ds, obviously. And I need the result, the probability, so I need the softmax for all the T's. And the T, I need the softmax for this T and for all S. And so the miracle here is that the dimension that we're taking the softmax over is the same dimension as the contraction dimension between the softmax and the V. So this S here, this it would be clearer as we need the softmax for this one T that is the output T and for all S. And so the miracle is that the contraction dimension and the softmax dimension coincide, and that enables the entire thing. In order to compute the softmax, we need the input to the softmax, and this is like a matrix product again, and it has as the contraction dimension just the hidden dimension here, the D. And here, this is also maybe interesting. When you feed it into the neural network, you have naturally the fastest moving dimension is the contraction dimension, which is much nicer than in MATML usually, because when you want read consecutive values, that's easy when you have the symmetry here in the operands. Okay, so we need for this one T that we want to compute at this thread, and for all the S, we need to compute this contraction. So if we ignore the softmax for a while, we could have the following tiling strategy. And in fact, this will be the tiling strategy, and we'll just have to mutate the softmax in. So we tile in this T direction, which is kind of the easy direction because it's the outputs. And we load a Q tile that matches to this. So it is tiled here. We load all Ds. And so we have, if you want, for this matrix multiplication, we have, in the contraction dimension, we have tiles that span the entire contraction dimension. And so if you remember how the tiles were all square when or in the next lecture, Jeremy, in more detail, showed matrix multiplications. Here you have contraction dimension, tile dimensions in D implicitly that cover the whole thing. So it's a huge tile. Yeah, more like an entire row or column. And so we load one of those Q tiles and we initialize our output, and then we need a for loop over the S tiles, which is kind of how we had this inner dimension. If you remember the matrix multiplication, the inner tiling dimension was the contraction dimension. And here it is the contraction dimension of the output matrix multiplication of the probabilities with V. And so here we load one of the K and V tiles in the S dimension to shared memory, and then we compute the logits and eventually also the probabilities of the matrix multiplications of the Q tile with the KT tile. And then we get logits, and we compute probabilities from that, and I'm glossing over this part. But then we update our output with the matrix multiplication of this weight matrix that we just computed with the v tile here in the last row in this inner loop. And when we're done, we just write the output tile. So this is really kind of an advanced tiling because we're kind of mixing the tiling ideas of the two matrix multiplications. But things align nicely enough that if we solve this gap to go from P to L, and if we can deal with these giant tiles with the D dimension, then we're good to have a tiling that works conceptually very similar to the matrix multiplication one. So Mark, if there's if it's all too if I'm glossing over bits, you keep me honest, right? So if you have questions, do interrupt.
Yeah, so like I do think like at least when you're explaining what P and V are, like basically you have like L, Q, K, like just basically the path of all the intermediates might need like a picture. I think Hugging Face had a really good picture on this, so let me see if I can find it and post it in chat. Just give me 1 second.
I'm terrible with the pictures. So I have the picture that Trudeau himself has in the paper. It's not probably not the step we want currently. But yeah, so the idea is that no, I don't like that.
Not for this one. I'm sorry, I realized I was muted. So I did share like a really good picture in chat. So if you want to open that up, I think it'd be very, very helpful to go through that picture with people.
Yeah, let me get the chat.
You want
this one?
Yeah, that's right. Just because it makes the intermediate like S and O and T and stuff like that. Like I think some of the terminology gets lost without a picture. So I really like this picture. It sort of makes it very clear what the standard versus the Flash implementation is actually doing.
Oh, yeah. So basically, okay, you have writing a lot, but to my mind, this is just the way of saying, well, we fuse things, like we load all the inputs, and then we write all the outputs. And if you see here, actually, and this is maybe an interesting part here, this explains FlashAttention 1. And you can tell that FlashAttention 1 had the organization such that they had to write intermediate outputs O, L, and M to the DRAM. And FlashAttention 2 got its speed up from avoiding that as well by rearranging the tile order. I skipped the old picture, but basically the FlashAttention 1 more or less swapped these two tile orders, and that made some things a little bit more complicated.
Thomas, yeah, you might want to just share your full screen again, just like so we get the full screen real estate. I don't know.
Yeah.
Was it disabled?
I have to.
Yeah, perfect. Thank you.
Yeah. Okay. So the thing I skipped over here in this little short code, and I'm really a pseudocode person. I don't know why, but That's just how it is. Okay, so the bit I glossed over is the softmax bit. And so the formula we need to compute is simple enough. In order to get the probabilities, we need to compute the exponent of each component, and then we divide this by the sum of all of these. And because the output of the exponential function is always positive, if we have a real argument to it, then this is always between 0 and 1, and also it adds up to 1 if we add all the PIs, so we get like probability weights or likelihoods or whatever you want to call it in this context. But so probabilities in the sense that it's between 0 and 1 and they add up to 1. And this is nice enough, the output, but the problem is that these things can get really large or really small, the numerator and the denominator, and this is numerically not stable. And obviously the exponential functions, if I input like 100 or 1,000, that is already a huge number. So this we have to stabilize, and so the stabilized softmax controls these by expanding the fraction, and I could like multiply here with the exponential of minus m, or I can just add it into the exponential, and this will be like the same result if we choose.
I'm sorry, I'm really trying to play whack-a-mole with all the server mutes, so please mute yourself. Like,
Okay.
It's like it's been
so,
like
okay, if there's something, you interrupt me more forcefully than that was, okay? Okay, so if we do this with the maximum over all the LIs, that is nice because suddenly these terms we have in the numerator, they lie between 0 and 1 themselves. And the largest one obviously is just 1 because the argument is 0. And so we have a really really easy stabilization here. The problem is then that we need to figure out the maximum and then apply it. And so there's an online version of this where we think, yeah, well, if we have this, we can also update this incrementally by observing that if I want to replace the m here, Li is logits. And if I want to replace the m here with a m new, I just need to adjust whatever I have summed up so far. And so this is like a really, really neat trick that I can swap out the m, and so the idea is that whenever I have a new m, I adjust my outputs. And in fact, in the pseudocode that the FlashAttention presents, this is done block by block. And I'm always thinking whether it actually is the best way to implement, because sometimes it would be conceptually easier to just implement this element by element, but then you have lots of compute because computing the x function is not the cheapest function to compute. Okay, so this is why we need the stabilized softmax. Yeah, we need the stabilized softmax even for float 32. Before there was float 16, float 32 was like the less stable data type. And so when the exponential function is involved, arguments get large so fast that we need the stabilization in order to have good weights. And in fact, if you follow the PyTorch dev forums, just to give you a sense like how sensitive this softmax calculation is. It is a good question. Why do we need the stabilization when 32 bits are plenty? But if you want to know like just how sensitive this computation is, you don't need to believe me, but if you look at the PyTorch dev forums, I think just last week there was a post called fused multiply add.
I think that's the horse one.
harmful.
Yeah, you found it. Yeah, that one.
Here, yeah, FMAs and softmax and floating point considered harmful by Horace. And it's an awesome observation. And so the rounding differences between fused, multiply, and add, FMA, and possibly unfused multiply and add is the rounding differences there are large enough to make it a problem in the softmax for the FlashAttention. And so this is still, even if we have 32-bit floating points, it is quite sensitive. Okay, but I didn't want to bore you with math all the time, so let's see if there's something we desperately need. Yeah, so here we have like the limitations again, and I wrote this with index notation, which I'm not going to read to you. But so there are quite a few like additional things that go into the proper FlashAttention 2 implementation. So with masks, you have a non-rectangular block layout. So you want to be clever about allocating your blocks to workers too. And the FlashAttention 2 paper goes into some detail for that, and it uses different strategies for forward and backward. Also, like in order to be able to utilize tensor cores, FlashAttention uses Cutlass, an NVIDIA library that implements all sorts of matrix multiplication primitives with tensor cores. And this will be thankfully covered in a later lecture because it's obviously a lot too large for today. This makes FlashAttention 2 like a very, very large C++ file to compile. So I chatted with Alban from PyTorch fame, who is one of the two people who answer more questions on the PyTorch forums than me. And so he said that the FlashAttention 2 file is the reason why he can compile PyTorch on his laptop, because it uses like 40-something gigabytes of RAM to compile FlashAttention 2. And so the tiling options that they mention in the paper are basically you can have tiles of size 64 or 124, which are quite large already. And I haven't been able to reach these yet. But so they say they have these tiles, and so they have 4 visions, and you could auto-tune that, but it's they manually did that for the paper. Okay, so with this, I went and tried to implement it in Numba, but we hit shared memory limitations very, very large, very, very fast. Obviously, for those that just want to modify a bit about FlashAttention, I should mention that there is a great Triton tutorial example and template which you should look at. But obviously, this would be just half the fun, and so I went and tried to implement things more from scratch, and I can show you like how far I got, and maybe it's also neat to look at like the differences of implementing this in Numba versus implementing it in CUDA directly. So what I did is I took the FlashAttention forward pass pseudocode, and I'll just point out some things. It obviously is an awful lot of notation. But by the way, I'm running this in a Lightning Studio, and I need to do some advertisement for that because I'm now working for them. And obviously, I love it a lot too, because you can just show someone run this thing that I set up for you instead of installing things. But okay, the advertisement aside, I just took the FlashAttention pseudocode, and it will tell you to load tiles from HBM, the DRAM, to the on-chip shared memory. It will initialize like the outputs and the intermediate maximum values for the online softmax. It has the outer tile loop here that I presented on this slide earlier. It has the inner tiling loop. There it loads K and V. It computes this L matrix that I called L for logits. They call it S. And then they compute the online softmax and the output from that is just here very quickly. And because the output calculation and the softmax, online softmax, is in this contraction axis, I mentioned it several times that it's the same axis because that is on the same axis. They need to update the intermediate outputs with the same softmax adjustment trick. And so this is here the softmax, and then at the end you normalize with the denominator from the softmax, because this was always computed with the only the numerator multiplied. And then you also save the softmax here for the backward, which I didn't talk about. And so the first thing I did here was I just took some sample sizes and I implemented just literally the same algorithm. And if you look at it, it like looks not that terrible. Not great, but not that terrible. And I tried to name like the blocks similar to what they were before. We can run this and we can compare it. And note that I'm still doing this for a single attention head. But I can compare it to the PyTorch implementation, and that will just work, and it will yield the same value up to numerical stability.
So
Next thing.
So actually, Thomas, before you go on, like one thing I'm curious about, like given that you wrote the kernel in pure PyTorch, I would be very, very curious to see what the Triton kernel would look like for that after Torch compile. So if you could merge this code in our lectures repo, I can take a look at that, and if other people in the group are also interested, I think that'd be pretty.
I will definitely merge the code into the repo. So I would expect, and that is something that has been mentioned on the channel a couple of times too, that like the automatic fusion that compilers provide helps with the memory bound things, but not the more elaborate compute bound things. And I think this is like too complex for Dynamo to recover the FlashAttention kernel, if that's what you have in mind. But so it gives me kind of a reference implementation, and in particular, I can like also write intermediate results and things. And for me, this kind of, I don't know, I'm a mathematician, but for this kind of exercise, I like to have running code in Python as early as possible. And so that was this. And then the next step for me was try to translate that into a Numba kernel. And I don't think we've seen Numba too much here on the CUDA mode, but I think it's actually a very neat thing, because it essentially gives you almost all of the power of CUDA with the very much the CUDA semantics in a Python-style language, and it also has like a very rapid turnaround time because it doesn't compile through C++. And so what I did here is I allocated all these things in shared memory. And this is where I couldn't match the tile sizes, because one thing is I'm using 32-bit D-type, so I'm trying this on 32-bit. But also, while it says, the pseudocode says that K, Q, and V should be loaded into shared memory, it doesn't say anything about these things going into shared memory. And so they likely don't. And I'll show you a bit about that too. And so there are bugs in this kernel, unfortunately. But for my dinky little test case, and you call this kernel, you just decorate it with number CUDA JIT. And then you can write CUDA. Like, this is the thread IDs. Here are declarations for shared memory. And then I can just loop over ranges. And it looks like CUDA written in Python. So I can run this by specifying here block size, and I'm just using a one-element grid because I'm only doing one block here. And you can just pass the tensors, and this is made possible by magic. And this magic is like the CUDA array interface that PyTorch supports and that Numba supports, and that allows you to just call Numba kernels with PyTorch tensors, which wasn't the case in 1917. And so I'm just incredibly happy that this interop works now. And so we can run it, and we can see that, yeah, there is a numerical difference, but other than that, it computed the same for this small example. But so I mentioned that these should not be shared memory, and in fact, from what I can see in the code for FlashAttention, they should be in the registers. But so the convention is that if you access an array with dynamic indices, then you need to like lay it out as an array. But if you declare a local array and it's constant size, and you don't access it through, and you just access it through like plain vanilla indices, like for loop indices, then CUDA will allocate those into registers. And so this is what I tried to do here, like allocate low chunks of O. And I don't think I got that exactly right yet. But basically, you can now expand so I expanded the Python version to the Numba version, which still was like a little bit more compact than this. And so the crucial thing here is to get all the for loops right. And half of the time I'm hunting down where I like had the wrong looping variable here, and or the wrong condition here that didn't match the looping variable, and then the kernel would either hit an illegal memory access or just run forever. But so I translated all the Number code into C++ code, which also is not that deep. But I also rearranged it a bit in order to facilitate having O in the registers. And this is something that you should really think about. And to me, it's just incredible. You have like 48K of shared memory. So if you run the full block sizes, this will be used up by Q, K, and V. And I'm still having shared S here. So the outputs are allocated in the registers, and this is possible because we actually have a sizable register file on the streaming multiprocessor. It has 16K single precision registers. And so we can actually allocate a lot of registers here. So it's I think it's 200 something registers per thread that are that can be allocated, and so that's what we do. And in order to compile this program, obviously we saw a lot doing a PyTorch extension for that, and obviously that gets old after a while. So I tried to think about whether we can also use a new thing from NVIDIA called CUDA, Python CUDA, and they provide bindings for NVRTC, which is the runtime compiler. And the interface is a little bit elaborate. But you can compile this CUDA code to a kernel inline. And then the calling convention is a little bit worse than you would expect. And in fact, the official tutorial, which I've linked here, it says the following code example is not intuitive and subject to change in a future release. And so what happens here is that you need to have memory allocated for your various arguments that you want to pass to the kernel. Remember that we said that that would be allocated in constant memory. And so what we need to do here is we need to allocate tensors on the CPU that have the right D-type that matches our argument D-types. And we pass pointers to those to the kernels. And for the arrays, the tensors we want to pass in, those are CUDA tensors that we have. We allocate a 64-bit integer that holds the pointer to the underlying storage, so the data pointer. And then we have pointers to all these arguments in these three tensors. And those are the things we pass to the CUDA launch kernel function. But through a miracle, it all works. And except when it doesn't work. And it will work better when I start the code. So thankfully, this compiles really, really fast. And so with any bit of luck, I'm getting, it shows like numerical differences only. And that is when I run only part of the cells. But you also see that I'm considerably slower, even on this trivial example, I'm considerably slower than the built-in scale.product attention, which is something to work on. And I was even slower. I had like a 10 times factor before I moved the outputs from shared memory to registers. That sped up things a lot. But you have to be careful to not spill registers. And so this is how you use CUDA Python if you want to run kernels directly. And I want to.
So actually, Thomas, so a quick question. So, like, you talked a lot about like register spilling. But at least, like, I mean, even from my perspective, like when you're programming a CUDA kernel, like you really just control shared memory. Like you never explicitly say, hey, like don't use more than this many registers. So I was curious as you were writing this kernel, how were you going about detecting whether you had a risk of register spillover or not?
Yeah, so actually, you would look at the kernel afterwards. And so one thing I did is that I just pasted it into the Godbolt in order to see what's going on. And the next thing will be to run it through the NCU profiler. And you will get alerts about that. But obviously here with the amount of registers that we allocate here, that will be we try to really allocate as many registers as we can. But obviously there's a limit of 255 per thread or so. So
Interesting. So maybe I'll from now reserve my first question for the Q&A. You don't have to do it now, but like I'd be really curious as to how you detect spillover looking at PTX and Godbolt. But I'll just let you finish your presentation and we can get back to that point later.
okay. Question. I think there's a warning flag about that, but I would probably need to check again. So when I wrote the CTC loss kernel, the register use was huge too. It had like 50 registers per thread, and then if you have like a large block size, that is really a limiting factor. But okay, so we will have to look at that. One thing I wanted to show you also, because I'm so immensely proud of it. So as you might have heard, we launched Thunder at GTC, and so I want to plug this as a neat way to include your kernel into a model. Thunder is a source-to-source compiler for PyTorch. So what we do is we take PyTorch functions or PyTorch models, and we just call ThunderJIT, similar to other JITs, and then you can just run the JIT function with the same things. And here, just for testing, I took a trivial function, but you could also have like a neural network model that includes this. And so the neat thing is that we can now say, well, we have implemented our kernel here, our custom one. We can register this as an operator with Thunder by providing like an implementation that does the actual thing on tensors, and here a little meta function that just tells you what kind of shapes are returned from the thing that I call with certain inputs. And if I do that, I can then say, well, yeah, now my super awesome new attention kernel that is not quite faster than the standard one yet, that can replace the torch scale.product attention kernel. And I can provide a function that kind of does the replacement, which is this transform function, and it has the same signature as PyTorch standard attention. And it just calls my new attention operator that I registered here above. And then you get a checker function where you can actually provide conditions which you want to have in order for your replacement to be used. For example, I didn't implement causal or attention masks or dropout yet. And so whenever that happens, I just return false. I don't implement multiple heads, multiple batch sizes yet, so I'm dropping out for that too. And then if I register this, and I just run it, it will automatically replace this call to dot product attention with my attention. But if I do something that's not applicable, then it'll just run the standard PyTorch thing. So once you have your super optimized kernels, which obviously you will produce lots of optimized kernels after all the lectures, and hopefully my kernel above will get a revision too. But so you can plug these into your model in order to like do comparisons really easy too. So this is kind of the thing I wanted to tell you about Thunder. Thunder is also kind of the reason why the preparation time was a little bit short. I hope you kind of have an initial feel like how FlashAttention goes about doing it. And I hope to, I will send this version of the attention, but I hope to have a little bit more sophisticated one too, with a little bit more time. So this is what I wanted to show you, and it's about time that I finished talking too. So if you have questions, comments, go ahead.
Thank you, Thomas. Like, this was fantastic. Like, I actually, like, one highlight for me was like that you showed, like, basically you're like, okay, I'm gonna take a stab at writing like a FlashAttention kernel, and here's like the diff between like my kernel versus like the actual sort of production one. But I also think it's such a informative exercise to go over and try to get that gap to be as small as possible, because like I would imagine that there's sort of like a lot of low-hanging fruit, and then some techniques might be hard, and that's fine. You know, we don't include them, but just having like this sort of very educational yet performant kernel that people can just step through a debugger, profile, and CU, look at the PTX is just, I think, going to be very, very helpful for the community. So thank you so much for that. Like, folks, please give Thomas like a giant like round of applause, like emojis. And yeah, like Thomas said, like, you know, we can start going over questions as well if anyone has them in the audience. All right. Sweet. I guess like Thomas, while people are waiting for questions, I was like really curious to revisit the register spillover question, like from earlier.
Yeah. We have other questions that we can do first. And
Yeah.
Maybe I have.
Yeah, there's already one question. Like, are you replacing at the A10 level or at the refs level? I think that's a question.
So what Thunder does is it provides, similar to what I did here with the register operator, to this one. It does provide operators for the PyTorch functions, so it's very similar to the A10 level, but not necessarily. So you could also, if you have like, can say here this replaces, then you can say some other function that it will replace. And so Thunder has actually a Python interpreter built in that will redirect all calls into PyTorch to do the recording in this Thunder trace that I showed you a glimpse. And so the idea is that all our intermediate representation is like a Python code too, and you could actually copy paste that Python function and run it. This is kind of what we tried to do here is have something that's easy to use. You just run ThunderJIT. That's easy to understand, and this is the last traces here that you get Python programs for all the transforms. And if you look at like earlier ones here in this list of traces, you see that this is like the initial recording where it says ltorch scaled dot product attention. And then we wanted it to be really easily extensible, and this is why I had to show that to you too, because yeah, we think it's pretty good. Okay, so the register spilling. So the thing, yeah, now I have the godbolt on the other computer, but There it is for CUDA. And if I put in my no. And so you can see the number of registers somewhere. I have to see if I can. Oh, this was not what I wanted to paste. Does it look really bad? Full script. And so. And copy paste the kernel. Yeah, I should never do these things live because
I'm sorry, I know I put you on the spot, but like I was just really curious at it, and we could always like revisit it like in the repo later if it's too hard.
I mean, yeah, the official answer will be in the repo. But so I think there is a compiler flag. Yeah, so there will be. Thanks. I will, or maybe I get Luca on board, but I will gladly also present Thunder here, of course, if there's interest. The GTC lecture will be publicly available, but they have a kind of a delay. But there will be something. Okay, so in the compiler explorer, I always have to check if it's still on. It is. In the compiler explorer, you have you can see like you don't see maybe the reuse, but so the number of registers here goes way up. And obviously, one of the things that I should be doing is that I set the launch bounds for this kernel because it goes like all the way to 243 registers. And so I checked that at 16K registers, if I have a maximum, if I have like, I don't know, if I have 64 times 64 threads, it should be it should have like how many per? Yeah, I don't know. So there is a compiler flag where you can see it in the outputs if it doesn't show it anyways. So here it doesn't show it.
Oh, Thomas, I think it's all good. Like I can just like visit this like offline with you. But yeah, like it's just I thought
I have I think there is a compiler flag that will tell you how many registers it used, and so that will give you the info, and I'll include it in the notebook.
Sweet. Yeah, thank you. All right, folks, we'll give like maybe okay. You have another question? So as I understand it, in FlashAttention, we use QKV that are computed from input tokens by matrix multiplications. Would it make sense to fuse these multiplications into a single kernel as well, or won't they all fit into the same registers?
obviously you are at the very limits of what you can do in terms of fusion and materializing intermediates. Here, what people do is that they fuse like the three mud molds into one. And that helps a bit too, but no, you can't. I mean, obviously, at some point you're at this. What's the name of the company? Grok. They had like the thing where they have the entire model in shared memory or the equivalent. But yeah, I think for FlashAttention you can merge more into the kernel just because you have exhausted your resources.
So actually, yeah, like I mean, like fusing the QKV projections from the input matrix is a very common trick. I will say like there's been kind of one interesting research trend around like what are called like persistent kernels, which is you essentially have like a single CUDA kernel that represents an entire neural network. And it's persistent in that you feed it like different batches, and then the kernel will just do the whole thing. There is like I think
like
some work around
CUDA graphs or
yeah, like there's some work that some of the Intel GPU teams have been doing around this, where they have a single kernel for an entire multi-layer perceptron. It's an interesting research direction, and I think the constraint is register spillover, but that's a very shallow answer, and I do expect people to produce more of these kinds of mega kernels in the near future. I just don't know enough to say why they're not as widespread as I think they are. All right, so I don't see any more questions in chat. So yeah, let's just give like another round of like applause and thank you to Thomas. The lecture next week will be Andreas, who's going to be talking about ring attention. So it's a very natural extension of the stock, but to scale to infinite sequence lengths. And Andreas and a bunch of folks on Discord have been working on like basically a working group trying to re-implement like FlashAttention here. So I think I'm personally very excited to learn more about that. And yeah, thanks again, Thomas. Like, this was fantastic.
Yeah, I'm looking forward to the pro part from Andreas too. So see you all next week, and thanks for joining this week.